Hey, good morning, everybody. So I want to welcome you and Jeff to two inaugurations. One, this is the first of a series of talks on artificial intelligence, sort of the boundaries of the science that we're sponsoring with George Mason this year. We're opening it up, so I see a lot of Metronites here, but I know we have folks online that are outside of the company, so I want to welcome you as well. The other piece is, Jeff, you're our leadoff batter on our new conference room, so thank you for coming and helping us. I think we've already worked out all the bugs, I promise you that, so there will be we will not find a corner case for you in the next hour. You know, we're excited to both have a chance to learn from those that have been really the practitioners and pushing the state of the science through Jeff and the others that will be coming over the next year. And again, as we've all talked internally, you know, this is an area that is fairly obvious, a place that we have a lot of interest. We want to find out what's the right METRON approach to some of the issues that are being faced both in industry and in DoD. So with that, I'm going to turn it over to Chris to do the formal introductions, but I just wanted to welcome you and say good morning, everybody.
It's my pleasure to introduce today's speaker, Dr. Jeff Schneider from Carnegie Mellon's School of Computer Science. My connection to Jeff dates back to the early 2000s when Tom Mifflin and I collaborated with him on a series of R&D programs under DARPA, Homeland Security and the intelligence community, where we developed and integrated machine learning approaches from network pattern matching and community detection, exploiting entity link data, to a supervised learning technology that we customized to exploit cargo data and provide cargo risk assessment that we deployed operationally at Customs and Border Protection and Office of Naval Intelligence. Prior to Jeff's return to Carnegie Mellon last fall, he spent 3 years as the engineering lead for Uber's Advanced Technologies Group. And his talk today will be drawing from that experience as the lead on Uber's automated car driving program. So, Jeff, the floor is yours.
Great, thank you very much. It's great to be back here and see these guys after so long. It's awesome. I want to start just with a very small amount of history, right? So Uber came and opened its self-driving program in Pittsburgh in 2015. That's not an accident, right? Work on self-driving cars at CMU dates back literally to the 80s. And so there were a whole series of both on-road and off-road projects there. And the one many of you have probably heard about is the DARPA Urban Challenge in 2007. When they set up a mock city there for cars to drive through, and that's when Google kicked off its effort. But scrolling forward, in 2015, that's when Uber opened its self-driving car effort in Pittsburgh. Many of the faces here are folks that worked on those previous projects. I didn't. This is when I got involved in self-driving cars at this point. And so that's a little bit of the history. I want to talk a little bit about the motivation. So one of the reasons, there are several, but one of the reasons to look at self-driving cars is because accidents are actually going up in the US. So the 2016 and 17 were the deadliest driving years in a while. Almost 40,000 deaths in the US. So if you do the math there, that means just in the time it takes us to do this talk, there's going to be another 4 deaths in the US on the roads. And you can take, if you want the worldwide numbers, just multiply those all by 30. And so it's quite a serious problem. Of course, the government has studied this. In that graph on the left, the fine print there says the problem is the driver. 94% of these incidents, it was actually the driver at fault. And so this was further broken down into, okay, what did the driver screw up? And so the biggest category, 41%, is what's politely called recognition error. What that really means, you just weren't paying attention and you didn't see something that was important to what you were supposed to be doing. The other large category is called decision error. That, again, is a polite way to say you did something illegal, you were driving too fast for the conditions, or you just didn't understand what was going on around you. So those are the big problems that we hope to fix with self-driving cars and make the road safer. So how are we going to do that? So this is Uber's self-driving car. What it has on it is this thing's a robot, right? So it has all the sensors that any good roboticist would want to put on their robot. On the top, there's a LiDAR unit with 360-degree coverage. Right below that, you have cameras with 360-degree coverage. So LiDAR gets you accurate spatial location, right? Camera gets you high resolution and multiple color channels. And you can't see it, but there's also 360-degree radar coverage, which of course, lower resolution, but direct measure of velocity. So all these things together help us deal with that recognition problem, right? These things are on all the time. They're paying attention to everything. Of course, it's a robot, so it has all the other things you would put in a robot, a GPS, an IMU, wheel encoders. So that handles the recognition side of the problem. The decision-making side of the problem is the one that we really want to talk about, right? That's where the AI comes in. And so for the purposes of this picture, where's that? That's sitting in the trunk, right? There's a custom compute board there that's full of CPUs and GPUs. And that's where all the computation goes to make this car make its decisions. So before I get onto that, I think it's fun just to look at this. This would be a boring video in any other context until you put yourself in you put your hat on that I've got to type the code in that's going to make sense out of this and make the car do the right thing, right? It's complete chaos. You've got actors all over the place going all different directions, all different types. You've got flashing lights, you've got signs, some of them matter, some of them don't. It's complete chaos. And so what becomes apparent is nobody's going to sit down and type in the code to make this car drive at this point, right? We're going to use machine learning heavily throughout this system. It's the only way we'll be able to put this system together. And so what I'm going to do, I think folks here are probably pretty familiar with supervised learning, but I'm going to step through just a couple of slides just to give you sort of my mindset. How do I represent supervised learning in my head when I'm thinking about it? And so using images as an example, what do we do with supervised learning? Well, first we need to create the training data, right? So that literally means we take a whole pile of these images and we have a team go down and draw boxes around all the objects we care about, right? They literally just sit there at a computer and do that. And that's going to be our training data for this. And then what are we going to do with that? We'll have an image like this, and we're going to chop it up into individual training data points, right? So we'll pull all these things out. Here's a vehicle, motorcycle, and of course, much of the image looks like this, right? We need it to recognize that it's not nothing, it's a tree, but it's nothing we're going to worry about for the purposes of the self-driving car effort. Okay, so now we need to do supervised learning on this for images. Well, what does that look like? So I like to scroll all the way back just to have a, how do I represent deep learning in my head? I think of it like linear regression, right? So if you were doing a linear regression, you would have some input variable X, some output Y, and you want to create a model that will predict a Y from a future X, right? And the cool thing about linear regression, you can write down the error metric. If you want to use an L2 error, you have a closed form solution. You can find the coefficients and you're good. Okay, that's great. Except what if and of course you can do this in high dimensions as well, right? You can scale this up. That's great, of course, but what if the model's not actually linear, right? So what might you do? What you might do is invent a bunch of nonlinear features, right? So you might stick a sine of X in there, and maybe that will allow you to model this thing correctly. And of course, the cool thing here is it's actually still just a linear regression, even though you put nonlinear features in it. The model's the same, the error's the same, and the solution's the same. You get a closed form solution. What's the problem? Well, it only works if the model's actually linear in these features. And of course, you had to invent the features. So if you don't know how the features are, then you've got a problem. What could you do? You could go even farther. You could go to a nonlinear regression. Maybe the function's really this form here, which would be a nonlinear regression. So now you can fit a more complicated model. Now you don't have a closed form solution to fit the parameters, so you use gradient descent, right? And so that's great if able to compute the gradient. It's actually a differentiable function you have here. Gradient descent is effective in the sense that you don't land in a local minimum. That's bad. And still you have to figure out the features. So somehow things are getting worse, right? There's more caveats as you go down the chain here. So this doesn't seem like we're making progress. And whoops. So the question is, wouldn't it be cool if we could just choose some parameterized nonlinear function that we could just, it's powerful enough to just fit anything, and you can compute the gradient and gradient descent works. And so of course, that's what we try to do with deep learning, right? So in the most trivial sense, a classical sort of 1 unit machine learning algorithm looks like a logistic regression, right? You have these parameters, you can fit this with gradient descent. This is great because you get this nonlinear function, but of course it's monotonic, so you can't fit that many things. So what's the solution with neural networks? You stack these things up, right? You just stack all these functions up like this, and you use the chain rule to propagate your derivative from the error at the end all the way forward to the beginning, and then you can update all the parameters using gradient descent all the way, right? And so what was the big revelation in 2012? Okay, to really do images like I just showed you, we need a lot of these, right? We need dozens, even over 100 levels of convolutions, maxes, linear layers, all combinations of these. So you got millions of parameters. And the big revelation from 2012, of course, is that if you actually have lots of data, which we do thanks to the internet and other sources, and you have lots of cycles, which we do thanks to GPUs, and you do some careful tuning of these algorithms, this actually works. You can learn. But when I look at all the crazy neural net architectures in my head, I'm just thinking of that regression in the back of my head, like, oh, you're just doing regression. Well, that's really all it is. Okay, so what's the result of that? If all goes well, you take those examples I just showed you, and you end up with a video like this. These are common by now. And so here's the system recognizing these pedestrians. And so we use these kind of learned models throughout our autonomy system in order to get it working. Okay, good. So that was the end for deep learning. We're just going to use that as a nonlinear regression going forward. And how does that work? So what I'm going to do now is show you what does this autonomy system look like. So what we have here is we have all these sensors that are sitting on the car. And from our Uber app, we know where we're trying to drive to. And somehow we need to convert that into the signals we send to the actuators here, to the accelerator brake steering. And so still it looks intimidating. It's a lot of things to do, even with machine learning everywhere. So we break it down into these pieces. Okay, and so this starts with the maps and localization piece. So what that means is Uber and all the other large self-driving efforts, they're not going to drive anywhere they don't already have a detailed map of the scene, right? And so a map here means not your Google map like you have on the phone, right? It's a full 3D reconstruction of the environment that's everywhere you intend to drive. And what that means is you have GPS to help, but you're not counting on GPS, right? If it's not accurate, as it's often not accurate, you can still position yourself because you're taking all your current sensor data and exactly matching the 3D shapes to the things in your map. So you know where you are down to the centimeter, even if your GPS is giving you problems. So that's the first step. The car has to say, where am I? The next step is the car has to say, well, okay, now that I know where I am, who else is out here with me? So that's the perception system. So this is Uber's perception system. And so here's the self-driving car. All these things are the other cars that it's detected. And all these yellow circles, these aren't noise, right? These are pedestrians, right? There are actually that many there. You can see in the videos at the top, this is actually a herd of them coming across in front of us, right? It's a bar scene at night, so people are going all directions all the time, and we actually have to track all these pedestrians and recognize where they are, so we can plot our route effectively. And this, again, all of this is happening with supervised learning, with deep learning, based on people labeling these things, millions of these, and us running the training algorithm on them. Okay, so after you've seen where everyone is, the next thing you need to do is say, okay, well, what are they going to do next? And of course, you can do a trivial rollout of your Kalman filter, and that's good for a couple of seconds or so. But you actually need to predict farther than that in order to drive well. And so the way that works, you can see this here. So now in this picture, again, here's our car. And these other cars have lines coming out from them. Those are the predictions of where they might go. And you can see they're multimodal. So here, for example, this car might stay in its lane, or it might move over here to take a right into this shopping center. So we have to make all these predictions about where the car is going to go next. And again, here's the bar scene again. And what you'll see is here's our car, and you'll see all these pedestrians. And importantly, you see all these predictions going across these crosswalks, but you don't see any predictions going across this way. And that matters, right? Because if you have predictions going crosswise when nobody's there, your car is just going to sit there, and people are going to be honking at you, and you're going to be stuck. And of course, the opposite scenario is even worse, right? If you don't draw the predictions crosswise in front of you, but people really are going, that's an even worse outcome, because you're gonna drive even though they're there. So that becomes very important to get all of those exactly right. This also is a supervised learning problem. And the nice thing about this one is we don't need to pay or take the time for a bunch of labelers to draw boxes and images, right? Once we have the perception system, we can just drive around and let our perception system run, labeling all the objects. And now we take that log, and for every snapshot in that log, we have a bunch of actors, and we would like to predict where they're going to be in, say, 10 seconds. And all we have to do to get that label is scroll the log forward 10 seconds and see where they were, right? So now we have millions of training data, no problem. And so we use a variety of supervised learning algorithms for that, many of them based on deep learning. Okay. So having found everything else about the world around us, now everything comes together in the motion planning system, right? So now we know what all the other actors are going to do, and we know what we're trying to do. And so what will happen there, here we're just showing a lane change. So here we're gonna make a lane change. There's someone that's moving across in front of us we need to worry about. There's someone coming up behind us. We need to get the timing right for that. So the way that planner works is, that's just a cost-based optimization for the planner. We roll out a bunch of trajectories. We have a cost function, and we do an iterative LQR solution to come up with an optimal trajectory for the car to follow there. So that's how the planner works. Okay, so that puts everything together, and that goes to the controllers and it runs. And so this is actually an older video, but I'm going to show you, this is our system running again. And I want to show you this just because it's got a couple things in it I haven't mentioned yet. And, some of the things, somehow I made it stop, okay. So you see the lines on the road? These all come from the map, okay? So the map already tells us what lanes are out there and what they're connected to. So these arrows give the directions of the lanes, and it also specifies the connectivity of the lanes. So we don't have to figure that out in real time the way a human normally does. It's all just written down for us in the map. Same thing with the traffic lights here. Of course, we have to read the color of the traffic light in real time from the sensor data. But we already know where to look for the traffic light, and we've already encoded exactly which lanes each light controls. So we don't have to sort out all those kind of things that can be quite confusing, especially in Pittsburgh, although I'm guessing it probably is here as well. Okay, so that's the whole system running, or it was before I killed the video. Oh, there it goes, okay. Right, so this continues like this, and you can see again the objects with their velocity vectors. Okay, so it took me I don't know, 10-ish minutes to talk through this, right? And this is the simplified diagram, right? The real diagram has 100 boxes on it. And so we've got this powerful learning technology. It just sort of begs the question, man, that's a lot of code to write. Couldn't we just do that? Throw all that code and forget about everything else. Well, it turns out, yes, you can do this. So this is called imitation learning. And what you do here is you take your same car with all these sensors running, and you tell your test drivers, hey, just go drive around town and just drive the way you drive every day. And what that gives you is a whole pile of training data where you have, like, here's all the inputs, here's what the car saw, and when you see these inputs, here's what the driver did. We can just measure it from the actuators. And so now we have, again, millions of training data points that show this mapping for us. And so what do we do? We just run that same learning algorithm on it. There's some issues with data augmentation, so I'm going to just mention them very briefly. This one's not important. Let me get to the other one. Here's the issue. So any of you have looked at imitation learning before? It's unstable. What happens is drivers are too perfect. So they drive down the middle of the lane all the time. But when you learn from that, there's a little bit of noise in your model. And eventually your model will just kind of drift a little bit outside of where most of the other drivers have been. And suddenly you don't have much data there, so you're not quite sure what to do, and it drifts a little bit further. And it just unstably drives off. And it actually does this, right? We did this. It's very smooth, very like nothing's wrong, but just slowly loses the lane and just drives off. And so yeah, exactly. And so what do you do about this? Well, the problem is all your training data is here with this input image, and you don't have any training data here, but you definitely need to know what to do if you ever show up here. And so the problem is you don't have this image, right? And so what you do is you just do a synthetic generation of this image. You basically move it over. It's a little complicated. You can see we did a very simple model here, a flat world model. And you can see by doing this, here's the original. We get all these crazy artifacts and stuff, but we did generate an image which now has the center line in the middle of this. And you update the action that the driver took. You update it to put you back on the track that you were on originally. And so you add this data into your training data, and it turns out that stabilizes it. This is kind of a hack. There are other hacks. NVIDIA did something where they put multiple cameras across the front of it and used different camera images. There's a bunch of things you can do, and they work. Don't worry about this picture. All this says is we just grabbed a random common CNN architecture and plugged the camera images and the radar images into it, and did the imitation learning based on that. And so it turns out that works too. So this car is driving autonomously. This green check is what means that it's driving autonomously here. This is the traffic headed into the tunnels in Pittsburgh, and there's almost no software running here, right? The only software running is the thing that copies the sensor data onto the front of that neural network and copies the answers from the end of the neural network back onto the actuators, and that's the only thing running. And so this runs all the way up to the tunnels. There are merges. There are a few other things. This works fine. Turns out this works fine too. Don't worry about the speed of this. This is replayed from a log, so you can see it's 3x real time. But it is highway speeds, and you can see this is a log replay. So the upper right, that white autonomous, that's what means it's operating autonomously rather than manually. And so the same thing happens here. It's good, and this is literally the image it's driving from. So all those water drops, it's actually driving from that image. And we did verify that if you don't train it on images that have water drops in them, that doesn't go well either. So that's we tried that, and so this works fine. Now this arguably is just doing lane following and adaptive cruise control. the same thing, and Tesla does. It's not really exhibiting much complex behavior. And there are some people that said, well, you know, I think imitation learning can do like very simple things like that, but it can't really do anything complex. So what we did is we said, okay, well here, this one's funny. This is one of our early stop signs. And you can see it's so early, we don't even have enough data to stabilize the steering yet, right? The steering's kind of jittery. But nonetheless, we're following this car up to a stop sign. Here we are at the stop sign. The car in front of us takes off, then it's that one's turn. And then there will be a truck here. And then after the truck, then we go. And so again, there's no software there, right? It's not reasoning about who arrived first. It's not trying to take turns. It's just the neural network just spitting this out. And so, and the really funny thing is, it really is imitation learning, because the video was so jittery you couldn't tell, but it didn't stop at the stop sign. But it did what people do at stop signs. It sort of slowed down a lot and then just kind of looked around for an opening and took off. And so it was sort of true imitation learning in that sense. Okay, so where are we on this? What Uber actually did ultimately was stopped this effort and invested all their resources in that first effort, the one with all the decomposed boxes. And the reason for that was, although the first one is complex, it's understandable in the sense that if it does something wrong, you have a pathway to figure out what happened and try to debug it, right? Where this one, like I said, there isn't much software in there. You've got millions of weights, and we did some creative things on debugging this as well. We had some nice tools when it made mistakes to figure out. Usually the mistakes were actually in the training data, and we had some nice tools to find those mistakes. But nonetheless, there's a challenge here. And I'm going to come back to that at the end when I get to what am I doing now back at CMU, now that I'm back there. But let me just put this on hold for a minute, and I just want to tell you a little bit about how does our software development process work. Still, we have to write a lot of software. We have to get this thing on the road. And so this is what it looks like. You know, we go through all the logs, we find all the events, right? And that allows us to group all the problems we have and sort of prioritize our development efforts. So this would be like your classical data mining kind of algorithms, right? And then what happens is we find some problems, and they go to a software engineer and say, here's some logs. We did the wrong thing. We need you to fix these. And so what happens, here's a log replay. So you'll see there are two cars here. So one is what the car originally did when the log was collected, and the other one is what the car does with the new software that was added by this engineer. And what that does is allow them to replay a bunch of tough scenarios and make sure that they're able to verify that their change to the code actually fixed the things they were trying to change. And of course, then what they do, you have a whole regression set as well, right? You go through a whole bunch of historical examples and see that you didn't break any of those. And in fact, usually you have broken some of those. And so then you go through another iteration of fixing all those until you get something that handles everything well. And you can see this one is, there's a blinker there, so we deemed that we didn't leave them enough space the first time around. So this leaves them a little more space. After that, you go into a simulation environment, right? This one's an almost empty scene, but the point is you can control all the actors, and it allows you to do a much broader testing of the changes you make to your algorithm. If that goes well, you go onto the track. This is our test track. And the cool thing is, right, when the cars are on the road, they're really good, but they're not perfect. So there's a safety driver there, right? And in fact, almost always at the track, we have a safety driver driving as well. But it's a closed track, so so none of these cars have drivers. So they're all just moving around the track with so what you'll be able to see here. What you'll be able to see is just And so you can see here, I don't know if you noticed, he was just pulled across by a wire. They're all radio controlled now, so you get a little radio control thing and you just drive them all over the place and mess with the cars. We have pedestrians, we have bikes, we have all kinds of stuff that you can drive around to mess with cars. Okay, and so if all goes well, then that change to the software goes out on the real road. I show this one just because it's a tough one. There's a bike there, and we have the usual problem with a bike. Can I pass him now? Do I need to give him space? Can I pass him now? Do I need to give him space? Can I pass him now? Yeah, okay, and I can get past him. So this is just an example of having done lots of those interactions on the track and lots of those log replays. We're now pretty good with bikes in that kind of scenario, which is a challenge even for human drivers sometimes. Okay. I want to get to a little bit more about the research I'm working on now, but just to give you just a little bit of context, you know, where's Uber and all this? What you know, how far they've gotten? What have they done? So in the fall of 2016, they launched their self-driving car effort, and what that meant was when you called an Uber, if you were lucky and one of these self-driving cars were close to you, you would get this message on your phone. And what that would mean is one of these would come pick you up. And again, there was the safety driver was there. The cars weren't perfect, and sometimes they had to, you know, they had to intervene. But you got a ride in one of the self-driving cars. So, so we went ahead and launched that in Pittsburgh. This is what that experience looks like. The one in the front's for the driver, but the one back here is for the rider, and it shows you, you know, what the car's seeing. You see the car, you see all the other objects. And the cool thing about this also turned out to be a user adoption study, although not entirely intentionally. This button here says capture your moment. It's a selfie button. What it does is it takes a selfie of you, superimposes it on this picture, and then sends it to you. What we discovered is that when people rode in these cars for the first time, they were as ecstatic as you might expect. They would walk in and say, oh my gosh, I can't believe it. You know, the car is driving itself, and they have a million questions for the driver. What's that? What is this thing on the screen? Did it see that person over there? Million questions. Until they found the selfie button. And then they were so busy texting all their friends pictures of themselves riding in a self-driving car that they had already forgotten about how strange this experience was. This was already the new normal. And so I think in terms of user adoption, I think it's going to be really fast once these things are good enough to get the cars out. Okay, so just to scroll forward, 6 months later, we launched the same thing in Phoenix. Most of you heard about the incident in Phoenix about a year ago now. At that point, we pulled back many of the cars from the road, reviewed the whole safety program. That took about 9 months. And then as of December, we put cars back on the road, but at much smaller scale. So they're back in Pittsburgh in a more limited domain, more limited scale. Okay, I'm actually just going to skip this. This is some of the stuff about what the cars will change in the city, basically in terms of getting our time and space back in the city. But I'm just going to skip that because just for a note, lots of companies working on self-driving trucks as well. Uber was as well. They pulled back on this effort about 6 months ago, something like that, more like 9 maybe. Basically, the idea was let's get the autonomy software working first, and once it's working, we can always put it on the trucks and deliver freight as well. How far did Uber get? Well, it's actually quite amazing, right? In all this time, we drove 3 million miles autonomously with the car driving in the different cities we were in, and we gave 50,000 trips to just members of the public who asked for an Uber and got that message on their phone. So it's quite impressive how good the cars got. Okay, so what I want to do now is just switch gears. Okay, great. The cars are good, but why did I not have a self-driving Uber bring me to work today? They're not there yet, right? And what's left to do? The big one is the long tail of rare events, right? You can't actually pull the safety driver out until you handle all those edge cases. And And the problem we have right now is that's an extremely engineer-intensive effort. Every single one of them leads to that software development process I described to you, where they're replaying lots of logs, and for every one they fix, they often find another one they broke in the regression set. And then it's back to square one. Okay, now let's get that whole set working again. Very engineer-intensive effort. Same issue with, for this to be a commercial product, we've got to scale it across lots of domains, right? All areas of the city, many cities. I can promise you we're not ready to drive in Mumbai yet. It's, every city is different, and again, very engineer-intensive effort to make the system work. And then the last one is we need to do more work on validating and verifying the performance of AI in safety-critical systems. The reality today is, for all the success that AI has had, there's two kinds of systems out there. Ones that are not safety-critical that use AI, that's all the online stuff, or ones that are safety-critical, basically don't use AI. If you think of the Boeing incident, they don't really use AI in those planes. And still they have issues, obviously. So these are the things that are left to do. How do we get there? In short, my answer is we've got to go back to that question that I had at the beginning. Should we use that heavily engineered system, or should we use this heavily machine learning based system? And I think our only hope to get these at a scale that's really commercially viable, we're going to have to come back to that machine learning and AI based system and make that work for real. And so now that I'm back at the university, that's what I'm focused on. And so this just says what I just said there. The things that I'm focused on now are looking at reinforcement learning and Bayesian optimization and bandit style algorithms to automate the tuning and the modeling that goes into making the self-driving car work. And so let me just give you some examples here. Okay, we all saw the success of AlphaGo, right? And we know how that works, right? In a traditional game tree like tic-tac-toe, you can just build the whole entire tree, see who wins and loses, and work backwards to find the best play in every scenario. In Go, there's 10 to the 170 possible states, right? Making this whole tree is not happening. So what do you do in Go? In Go, what you do is you take a deep learning network to model your current policy. You initialize it by imitation learning. And you also have to have a model of the value network, of basically how good each state is. And so you can use those two networks now to do a very efficient search of that game tree and to do learning along those most promising paths. And so that's how a reinforcement learning algorithm for Go works. And then the question is, well, we want to do this for cars, right? So the problem with cars, of course, with Go, you don't need a simulator. The simulator is just the rules of the game of Go, right? Here we need a simulator. So that's what we started looking at. So here's one. This is just for fun. This is a reinforcement learning agent learning to deal with a stop sign like we showed earlier. The good news for reinforcement learning is that it's a different problem. Self-driving cars is a different problem than most of the research going on in deep reinforcement learning right now. Most of the research is going in these kind of games, like playing Montezuma's Revenge or something, where you're looking for some crazy sequence of actions that magically works. So you have very sparse rewards and very long time horizons. Self-driving cars is the opposite. We have very dense rewards. We know what we need to do. We know which lanes to be in. We know which objects we don't want to hit. And basically nothing beyond 20 seconds even matters in a car, because you can deal with anything farther away than that. So it's a much different reinforcement learning problem, but we have to have better sample complexity if we're going to get that long tail of wear events, because we just don't see them very often. And so, okay, right. So this is what I just said there: dense rewards and modest time horizons. The cool thing is we not only have a simulator, but we can run reinforcement learning algorithms doing off-policy learning So that means we don't actually drive the car on the road. We actually just use those logs, and we just replay them in our mind the same way AlphaGo does, and do the updates to our policy based on what we see. And the reason we can do that with self-driving is because we have good driving policies, right? We can have a person go out and drive around. We can even have our autonomous system drive around, and it will show us reasonable policies that give us good data to run the reinforcement learning algorithms. Okay, good. So that's one aspect of things. And so, great. But what about things where the simulator isn't good enough? Is there anything else we can do to use learning to try to improve this system? And for that, we use Bayesian optimization, which to a statistician would be experiment design, or you can think about black box optimization. And the idea, very simply, is that you have some function that's unknown to you, and you would like to maximize that function. You'd like to find this location. But the only tool you have to do that maximization is you can choose a value of x and run a very expensive experiment to find the corresponding value of that function. And so you need to choose your experiments carefully because you can't afford very many. So when does this happen? In machine learning, it happens all the time because we use these algorithms to tune the hyperparameters of learning algorithms. But where does this happen for real? It happens when you have to, this is the classic experiment design problem. You have an expensive physical system you want to optimize, but it also happens in simulation now. Simulations are expensive, and there's way more that we could run than we have the computational resources to run. So we have to choose our simulations carefully in order to do a good job. Let's see. I am out of time, so
take at least another 5 minutes.
Okay, great. So just to give you a hint, how does the Bayesian optimization algorithm work? So again, for that 1D function, what we do is fit a nonlinear regression to it. In our case, we use Gaussian processes for this. And what that allows you to estimate is the function, but also the confidence intervals for that function. And you define an acquisition function based on your confidence intervals. So a very common one would be upper confidence bound, which essentially means take the tops of these, and that is your acquisition function. And you run an experiment where that's the highest. So why do you choose that experiment? Because it's a place where you expect the function to do well, and your confidence intervals are wide, meaning you'll learn something by doing this experiment. So that's a very words-only explanation of the upper confidence bound algorithm, which the equation's there. So how does this look on this 1D function? This is the confidence bounds here. As you choose the experiments, right, it maximizes this gray curve. So now it'll put one here. Now this comes down. So now the max is over there. It does one there. You repeat that. And when you're done, whoops, went too far. When you're done, the right thing has happened, right? It's covered the function, but it spent most of the experiments in the most valuable part. Now that's great. Professors like to draw 1D functions and point at them. Can you do anything real with this? So we tried this out on a snake. So snake, 16 degrees of freedom, all nonlinear. The physics of friction is very hard to model. Pretty much impossible to, we have simulations of this snake. They're not good enough to develop controllers on, because you find one that works in simulation, you put it on the snake, and it just doesn't work. So what can we do? We can use that algorithm I just showed you. We parameterize the controller, and then we use that algorithm to pick experiments. So this is the snake. This is the blooper reel of the snake learning to get over this obstacle here. And so you can see this thing sort of thrashing around, trying to get over this obstacle. And what we did here is we decided, well, the tall one was too hard initially. We're going to give it a small obstacle and let it work its way up. So why do we do that? This snake is designed for like disaster recovery. Right? There's an earthquake, building collapses, something needs to go crawl through the rubble and find some survivors. Right? So it would be very common for the snake to encounter this scenario. It's in the building and there's some obstacle it needs to get over. And so what's very cool about this is that when the snake starts, it's able to just kind of hop over the obstacle, right? It just kind of does this. But through that Bayesian optimization algorithm that I've shown you, by the time it gets to the higher obstacles, what you'll see is it's had to figure out that the only way to get over that obstacle is it actually has to curl backwards over the obstacle like that. And so I think we're almost to the point where you'll see it start to do that. Yeah, it's starting to curl back now. And once, I think after this, right, here's one in slow motion. So you can see what it's discovered here, that it's got to curl over this obstacle backwards. It does. I think there's one more increment higher, but I'll just skip ahead here since we're out of time. If any of you are interested in Bayesian optimization, this algorithm, so one of my students just did his defense in the fall. His defense focused on increasing the dimensionality and efficiency of these algorithms. So they've been around for a long time and work in low dimensions, 3 to 6. But what he did is worked on a bunch of models that allow you to scale this up to dozens of dimensions, even 100. And he pulled it all together into an open source package called Dragonfly. So if you want to play with that, just to get some ideas on Bayesian optimization, you're welcome to do so. And so, sorry, I don't have a real summary slide, but I'll just stop there and just say I'm really excited about this because we've made so much progress in self-driving cars, but yet it is clear to me that self-driving cars may well be the first case where we use a really end-to-end machine learning system, and that's the only way to make a commercially viable physical product where safety is important. I think all this is going to happen in the future, so I find this very exciting. So thank you very much for your
So questions? There's got to be a few.
Yeah, I've got one. On your test range, when you have lots of cars interacting with one another, do you ever get sort of unexpected, emergent, maybe unexpected and undesirable emergent behavior, like gridlock, where since everyone is equally bold or shy, they can't sort of get their way out of it, whereas in real life, drivers will have different personalities.
Yeah, exactly. So this is, this I would argue is not even a long tail problem. This is just a different domain problem. Like I mentioned, we're not ready to drive in Mumbai, right? Because that's the permanent state of traffic there, right? And you've got to somehow edge your way through it. And the short answer is that problem is real and it's not solved yet. But there's an interesting sub-problem there that's fascinating, which is because what you really have is a multi-agent planning problem. You've got all these agents together, and they have to interact with each other, and at least at some superficial level, they're actually cooperative, but they're often quite adversarial. And even within these types of games, there's a dichotomy of approaches, right? If you write the whole thing down as a game, you would look for a Nash equilibrium, and you would play this Nash equilibrium. That's one approach. The other approach is I'm not going to look for the Nash equilibrium. What I'm going to do is do a learned predictive model of what I think the other people are going to do. And then I'm going to make a plan that's optimal for me, given what they're going to do. And it's quite a debate, which of these, in games in general, but also in self-driving cars, which of those algorithms is the more productive way to solve the problem you just described. I actually argue it's the learning-based one, but there are many people that have many different opinions on this problem.
On that track, you guys looked at shared intent, right? So all these guys are sort of expressing, this is my intent for the next 5 seconds,
right.
12, 20, whatever. Have you looked into how that kind of helps stabilize things as opposed to sort of guessing what other people's intent is?
Well,
machines?
Yeah, I I guess I'm not sure what you mean by shared intent. We do try to predict the intent of all the other drivers and passengers. And we actually try to predict not only what they'll do right now, but actually what are they trying to do? What goal are they trying to get to?
But if I take away the uncertainty by saying I'm going to take everybody that's a self-driving automaton and have them share their information.
Oh, I see. Share the information. Yeah, absolutely. So we have not put a lot of investment into that. The reason is what will happen in the future is that there will be lots of infrastructure there to support self-driving cars, to do things like, if you think about the traffic light, right? It's crazy for us to look at that light and say what color it is. The traffic light can just tell us what color it is. I mean, that doesn't make sense, right? So all that stuff will come, and then the communication between vehicles, that will come also from the development of standards so vehicles can communicate with each other. But most of these things have the government in the process for those things to happen. And so what we've done is said, okay, look, we can't let these uncertain things delay our progress. So we're going to develop the vehicles now, assuming we have no connectivity, no help from the infrastructure. And it's a little frustrating because we're solving a much harder problem than what we will have to solve once all that stuff is in place. But it's a race now to get the cars working. And so we just can't put those things in our critical path, at least right now.
So Jeff, do you see a path forward for public acceptance of self-driving cars?
I think it'll happen, and I think it will be. There's a lot of work to be done, but I don't think there's any doubt about the outcome. So that all the government agencies, basically everyone knows, there is no world where in 50 years from now, basically there are self-driving cars everywhere. And so it's just a matter of figuring out, how do we put the regulations in place to support this? How do we do the, whatever kind of verification, certification we need? I think that there's a lot of work there, but it will happen. And the interesting thing is, because different government jurisdictions have different appetites for that, ultimately the development efforts will just go to those governments that want to support the development efforts, and they'll start there and they'll go from there. Yeah, all the way in the back.
Can you say a little bit about what part of the long tail is created by bad actors, pranksters, et cetera, and how to deal with that, or how you anticipate it'll be dealt with?
Yeah, there are definite bad actors out there. Those are some of the long tail, but I would argue that the problem Tom mentioned is actually a more pervasive hard problem. The close interactions of good actors are much more common and still not yet solved than the occasional bad actors. Although we do, believe me, once you put a camera and a LiDAR on top of your car and drive around, you will see every crazy response to that you can imagine.
I can show you some roads where every mailbox has been hit.
Yeah, yeah, exactly. We have, cars intentionally cut us off just to see how we respond. All kinds of things. Pedestrians. We've had pedestrians come up to us and bang on the hood. I mean, you see every crazy thing imaginable. So we'll have to solve those, but I don't think it's the largest one to solve.
How robust are the current approaches to a changing environment? So, a four-way intersection gets changed to a roundabout, or you get potholes that develop on a road that you want to be able to navigate around.
The potholes are okay. We can detect those. If you change the actual road structure, essentially we have to change them. We have to update the map to reflect that.
You indicated that they're only driving where the 3D structure is known. Yeah. Do you think we'll get to a point where that's not a requirement in the near future?
Yeah, we can definitely do that. So the imitation learning one I saw you doesn't have a map. So it's definitely possible. I think we'll get better at that, but a map is one of those things that it's actually not that hard to build. And it's kind of why would you not benefit from that information? What we'll do is just get more robust than we currently are to mistakes in at the map. Right now, essentially, when the car sees that it doesn't have a good match with the map, it basically just stops it. Thanks for help.
How would you see, like, one company dominated the self-driving car market? There's so many accidents. How would they handle the legal liability for all those accidents?
Yeah, I think the legal liability is yet to be sorted out. My hope is that the legal framework for self-driving cars turns out to be closer to how it is for airlines than how it is for the medical system. And if you think about those two, one of those, arguably works okay in spite of recent events. The other one is a mess.
Sorry, along those lines, did you ever wrestle with ethical dilemmas, like a car is faced with a choice between hitting a pedestrian or an oncoming car?
Yeah, so we'll have to deal with that. Yeah, so the common word for that is the trolley problem.
Right.
We'll have to solve that eventually. The way I look at it is there are almost 40,000 deaths a year in the U.S. and virtually all of them were not the result of a decision somebody made on the trolley problem. So we'll work on all those first, and once we get all those smashed down, we'll have to really get into some of those ethical questions. So I think it'll come. I think it's just not the one we need to sort of get from the beginning.
We've got a number of
We've got
questions.
three questions online.
Okay.
First question, redundant hardware compute processing systems in the vehicles in case of failures.
Let's see. It is a system with multiple CPUs and GPUs. So it fails gracefully in that sense, but the reality is any failure of that sort is going to result in the car just pulling over and calling for help.
Okay. Second question is a prediction reliability question. When the car is not certain about its environment, what are the mechanisms to detect the uncertainty and let the driver take over?
Yeah, so with the certainty of the environment, so all the things that I showed you in the videos all come with probabilities attached to them. So all the predictions of the different pedestrians, cars, there's a probability that that's what it really is, and also when they predict where they're going to go, you get a multimodal prediction of where they might go, along with uncertainty about each of those paths. And what happens is at any point where the motion planner is unable to come up with a plan that it feels is safe given all the uncertainty it's presented with, it'll kick out to the driver and say, hey, take over now, I'm not sure what to do.
Okay, and the final question, seems that retraining to handle edge cases is engineering intensive. Would having some hard-coded rules reduce the number of edge cases?
You can fix some of the edge cases with rules. The problem is that the rules are also what causes a lot of the engineering complexity, because the reality is the system right now, all those boxes, although they're sprinkled with learned models everywhere, a lot of the glue that's connecting those learned models are essentially rules. And it's actually the crazy, unpredictable interactions between the rules that causes it to be an engineer-intensive process. So we use some rules, and we'll continue to do that, but I think it's adding rules is actually a complexity increasing rather than decreasing activity.
Do you have plans to partner with car manufacturers to offer sensor packages that would give you the data that you need, on not just your own cars, but consumer vehicles?
We have various partnerships with the car manufacturers. I mean, obviously the big one is Volvo. Our cars are Volvos now, but we've announced some with other ones as well. We don't really need that to collect data so much, because it's actually, our fleet's big enough where we can just drive around ourselves and get a ton of other data. The bottleneck is really labeling that data. And so we don't need to partner with them at least for that reason so much. Although just sharing basic engineering specs and things like that, some of that is useful just to get good models of the other vehicles. There's another question.
When you do log file based regression testing. Presumably, once you start making different decisions, you'd expect different inputs than what you recorded in the logs. You have to do something to make that actually useful.
Yeah, so that's exactly the limitations of doing that. Without a lot of work, you're just stuck with what happened there. So it's good for checking very small deviations from what you did, but anything significant, especially anything that would substantially change the behavior of the other actors, at that point, you've got to switch over to the simulation where you can program some behaviors into the other actors.
You haven't said how big your neural network was or how many layers there were, but it's very common to read of tens of millions of parameters that need to be trained.
Yep.
I don't think you probably have tens of millions of data points. You may have a lot of data and you have a lot of computational power that certainly wasn't there even 10 years ago, 5 years ago. But you're highly over-parameterized, and yet, so how is it that you're able to learn anything that works well, especially when you get when you mentioned the limitations of imitation learning? Is that an aspect of it? So how do you justify training tens of millions of parameters given less data than that?
Yeah,
but still lots of data.
It's actually not quite that scenario. So if you think about, ImageNet is the classical like benchmark for academic things, right? And so the common architectures that do well on ImageNet, as you said, millions of parameters, some of them tens of millions of parameters, and ImageNet itself is order millions of examples, and those get the best results for ImageNet. So we are using essentially the same architectures that are popular for ImageNet, but we actually have way more data than ImageNet in training data. So although it's the problem you have is very real and it's there, we're actually in a better place than just using ImageNet as the example. We're actually in a better place than the things that are done in ImageNet.
How do you explain your success in that case? Your data, somewhat data poor, but parameter rich, and yet you still have success. How do you explain that? I'm not disputing the success.
Yeah.
How do you explain it? That's a very important.
Well, I think there's, at least with our labeled data, again, we're not as data poor as, say, people doing ImageNet. So one explanation is if people can do well at ImageNet, we're definitely in a much better place to do better than that. How do you do in general? In general, how do you get these millions of parameters to not overfit on insufficient training data? I think there's a lot of ongoing research in deep learning to try to understand why that's the case. There are various algorithms people use that are believed to help with that. People use dropout as one of the algorithms that's believed to help with that and just making the learning more robust. People use batch normalization at each of the layers, which is believed to help make it more robust to keep all the gradients down to a reasonable size. In the end, these are all different ways to do a regularized regression problem, right? So if you think about just a plain old regression where you don't have enough data, you might, do a ridge regression, or you might, or maybe you do some sort of L1 penalty or something else. You do some normalization to make that learning stable. And so deep learning, we have to do the same thing. It's just at the scale, we understand in a sort of intuitive sense the regularizing properties of it, but it's not, I would say it's not rigorously understood how that, how that really works. Sorry, if we need to stop.
No, we'll go a few minutes.
I'm happy to, yeah.
Just one more. You're saying how the example you showed with a car where there were droplets on the camera was a different state. Do you have to assess your environmental conditions and shift models, like learn models based on them? And how many different sets do you think you need to have?
Yeah, in that case, we did not. We just put in lots of training data of both cases. And at least for the example of rain, I think that is the most efficient way to do it because there's a lot of what you need to learn that is sort of common between the two, regardless of whether there's raindrops on the glass or not. But So for the most part, we try to fit it all into one model. But I can imagine going forward that we reach a point where we have even more orders of magnitude data than we already have, where we start to say, well, hey, it might make sense to learn specific models for different things. So far, it's all one model.
Got 2 more questions online.
First one is, how do you determine the probability threshold between certain and non-certain?
Right. So all these certainty thresholds, these are effectively some of the rules I was talking about. When I said there's essentially a bunch of rules that are the glue holding all those models together. That's what they are, and that's part of the complexity of the current system. They're ultimately tuned and tuned by going through all the regression testing and understanding what works best on cases.
And the second question is, have you tried to interpret the learned model?
Only in fairly limited sense. So what I can tell you we did with the imitation learning that was pretty effective was we would go out there and we would find a case where the car behaved poorly. And so this would be the classical thing, right? In the engineered approach with lots of boxes, you just go through the code and you sort of step through the log and see exactly what logic happened in the code till you find where the mistake was made. In the big black box model, right, there is no code. There's nothing to see there. What we were able to do, though, is we could take the activations of the neural networks at some of the interior levels and compare those activations just in like a L2 distance to the activations on each of the training data points we have to find the ones that were similar. And so essentially what we were doing is saying, for this scenario that you made a mistake on, which of your training data did you think was most similar to that scenario that was kind of driving your decision? And so that was very effective, and usually what it resulted in was us finding mistakes in the training data. And often just removing those training data points and retraining, and that would fix the problem. So that's one example, but there's a lot more work that needs to be done on that.
A follow-up question to that, what is the training process? If you have 10 cars, do you train them separately or combine them into one data trained model?
All a single model. Same thing there. Maybe at some point there will be car-specific ones, but our goal with the hardware was to make them as identical, at least post-calibration, as possible. So that.
Well, Jeff, I want to thank you for the team. Great talk this morning.
Thanks.
It's great to get a chance to really sort of hear what's at the cutting edge right now and where things are going. I believe you're available if folks want to stick around for a small group forum after this, but I think what we'll do.
Break until 10:30.
Okay.
Reassemble. Those that want to discuss with Jeff, let's reassemble here.
Okay. So I'm in learning mode. I'm learning what the schedule is. But yeah, we'll take a break. So 10:30, we'll get back together. If you're interested in have more of a small group discussion, Jeff's willing to stick around and chat with us for a bit this morning. But before we break the big room, I want to thank you with a little bit of a couple of METRON mementos. So, from us, thanks for coming. So what we have in here are things to support both your analog and your digital learning. So we've got the great METRON journal notebook when you want to go pen and ink, and we've got the power pack for a computer when you want to go all digital.
Awesome.
So thanks so much.
Thank you very much. Great.
All right, thanks everybody.